All right, Calculus 2. I'm still in section 6.2. We were learning about population growth. Here's another one, Newton's law of cooling. There's only a couple problems toward the end of the section about this, but I like this a lot. I'll assign something like this. So here we go again, an English sentence that we can translate into a differential equation. Here we go. The rate at which the temperature of a body changes over time. The rate at which a temperature of a body, we'll call that capital T, changes over time, which we'll call little t, so I'm using a couple different t's. The rate is the derivative, of course, dt dt. The rate of change of the temperature with respect to time. The rate at which the temperature of the body changes over time is directly proportional to, so we have a proportionality constant, the difference in the temperature of the body and the temperature of its surrounding medium. So it's proportional to a difference, the difference in the temperature of the body and the temperature of its surrounding medium. So that's the difference, the subtraction. Now, what we do in this problem is the surrounding medium is the environment that it's in, and we assume that that's constant. By the way, K is constant. K is a proportionality constant, but that M is constant. So the temperature of the surrounding medium we assume to be constant. Although in some more advanced differential equations, you could have that be a function of t. You could have that be a variable. But we're going to assume M is constant. And then we can solve this differential equation. We can solve this differential equation. It looks a lot like the last one, a little different. I would separate and integrate. That's our only technique we know. I would grab that whole quantity, t minus m, and divide down here. So I get dt over t minus m. I leave the k there, and I multiply by the dt, the little dt. So on this side, my variables are capital T and little t. K is a constant, M's a constant. On this side, I integrate with respect to capital T. You know how to integrate that. That is the natural log of T minus M. On the other side, you integrate with respect to small t, time, and you get KT plus C. This looks a lot like the last problem. We want to solve for capital T, the temperature. We want to solve for capital T, so we E both sides. I E this side and I E this side. When I E this side, I cancel the log and I get T minus M, and I lose the absolute value. I'm just going to lose those absolute value signs. On this side, I get this E to the KT plus C, but I've done this cool thing where we call that, if you remember, we call that E to the KT times E to the C, because multiplying the bases is adding the exponents, and therefore the e to the c becomes my new arbitrary constant c. So this becomes c e to the kt. And then I add the m to the other side, and this is the answer. So it looks a lot like our population growth, but we have this added m, and m's a constant. So that's the model for Newton's law of cooling. It comes from this sentence that assumes the rate at which the temperature of the body changes is directly proportional to the difference of that temperature in its surrounding medium. And it turns into a differential equation, which we solve, and then we have this model. All right, so I'm going to get rid of the sentence. I'm going to try, maybe I'll try to do a problem here. But the classic kind of problem, we can do some different kind of problems, but the classic problem is a time of death problem, where we say, okay, we found a dead body. So we find this dead body of a human, maybe a professor. We find him in the college classroom, and the classroom always remains a constant. Let's say, they keep the AC on pretty. Classroom is a constant 62 degrees Fahrenheit. So that's the environment where we found this dead body. So hang on, we found this dead body. Let's say it was, we found him at 11 a.m. And the first thing we have to do is take his temperature. So we took his temperature, and his temperature was 79 degrees Fahrenheit. So then we called the cops. The cops came, and they got there half an hour. So that means they took the temperature at 11:30 a.m. They got there, they took the temperature, and they found out the temperature was 71 degrees. And the question is, find the time of death. So we don't need the differential equation. We're going to assume that this follows Newton's law of cooling. And we are going to use this model. We've got some data. The data helps you find the constants C and K. One of the constants was given. The temperature of the room is the M. That's 62 degrees. We're going to have to use this data to find C and K. And we'll be able to answer this question. Find the time of death. Oh, the idea is that when he died, he had a healthy, normal body temperature of 98.6 degrees. After that, he laid in this cold room and his body began to cool off. So after so much time, it cooled to this. After a little more time, it cooled to this. So we're going to go backwards and try to find the time of death. So I would set this up like this. It's cool to have t equals 0 in your problem. And I would call 11 a.m. t equals 0. The temperature was 79 degrees. So I like to organize my data. And then 30 minutes later, and I could do this in minutes or I could do this in hours, it doesn't matter. I think I'll do it in minutes. 30 minutes later, the temperature was 71. So there's my two pieces of data. What I'm looking for is some time before 0, I guess it'll be a negative time, when the temperature was 98.6. I'm looking for the temperature, that's a question mark. I'm looking for the temperature when, I'm looking for the time when the temperature was 98.6 degrees Fahrenheit, when he was alive. After that, as soon as he died, he began to cool off in this cold room. All right, I'm going to use this model. You know, in our previous problems, population growth, good old exponential growth, whatever was corresponded to 0 turned out to be the C. Not true here, not true here. With that M in the problem, you got to do just a little bit of math to find C. So this piece of data will help me find C, but it's not 79. Let's see what it is. We're going to plug in 79 for the temperature. M is 62. We don't know C, we don't know K, but we just plugged in a 0 for the time. And by the way, we're calling that 11 a.m. Okay, all right, so that's e to the 0, that's a 1. I can find C, I can subtract the 62. I think C is 17. All right, that was easy. This next piece of data will help me find K. That's how it works. What am I going to do? Plug in a 71 for the temperature, 62. I now know C is 17, e to the K, I don't know K, but I'm going to plug in 30 for the time. I'm going to do the math again to find K. If you don't mind, I'm going to do 6 algebra steps at once. Subtract 62. What's that, 9? 9. Divide by 17, divide by 17. Take the ln of both sides, and then divide by the 30. I guess that's K. I think I did that right. Subtract 62, 9, divide by the 17, take the ln of both sides to kill the e, and then divide by 30 to get K. I'm going to pick up my calculator and see what this is. This is my K, although there it is. I can just use that number, but it's some kind of a number. It is the natural log of 9 divided by 17 divided by 30. So I get a little negative 0.021199, little negative 0.021199, 625, anyway, I might just use that number. There it is in my calculator. Let's see, I think I have the model now. I have the model. I'm going to get rid of this. Got a little more room to work here. The model is this model. The temperature, unknown temperature at any time is this 62 plus this 17 e to the k, I now know k, natural log of 9/17 over 30 times t. So there's the model, and again, if somebody gave me a time, I could tell them the temperature of the body. If somebody gave me a temperature, I can find the time it takes to get there. So that is the question. The question is, when was the temperature 98.6? And it's going to be a negative time. It's going to be before zero. So many minutes before zero. Let's see what it is. I'm going to plug in 98.6 for the temperature, and I'm going to solve for T. Solve for solve for this T. All right, here we go. We need a little bit of room here. Again, it's all algebra. We did the calculus early on. We solved the DE in general, and now I'm doing all this algebra to answer these questions. I'm going to subtract that. Subtract that. It's whatever. A calculator might help, but I think I did that right. 36.6. I'm going to divide by 17. I'm going to take the log of both sides, and then I'm going to pause. So I get what I just did was subtracted that, divided by 17. I took the log, which killed that e. Now I'm left with that log of 9/17 over 30 times t, and I want t. So I'm basically going to divide by that. That's my k. You know, one way to do it is multiply by the 30 and divide by that ln. So I don't know, whatever. I like to do my math a lot of different ways, but here it is. Here it is. This is the time. I'm going to pick up my calculator and try to find what that is. Hang on, hang on. We could be good detectives here. Hang on. The natural log of 36.6 divided by 17 times 30 divided by the natural log of 9/17, the natural log of 9/17, and the answer is, wow, negative 36.2 minutes. So that's awesome. I would say the time of death was, remember zero was it was 11 a.m. at zero, so negative 36.2 minutes. 10:24 a.m., rounding to the nearest minute, rounding to 36 minutes. 10:24 a.m. Wow, that's pretty cool. I like that. You should like it too. Again, very algebraic. We'll have to get a little more, do some more calculus here soon. Chapter 7 will be awesome calculus, but we're getting through some differential equations. These are really cool. All right, good luck.